What's up, everyone? Thanks for coming out. I know this is the second ledger talk of the day, so I'm glad we got some ledger nerds around here. I want to dig in some more, so let's do the intro here quick. So hey, I'm Corey. I work at Affirm, but usually I'm like self-effacing enough. I want to like blast right through this slide, but I actually got to talk about it for a second because it's super important to the story I'm going to tell today. So the important part here is previously Braid. So I was the technical co-founder, first engineer, eventually CTO of Braid for the last 4.5 years. And we, unfortunately, deceased startup. We had to shut it down earlier this year for a whole lot of reasons. It's a whole other talk. But the story I'm telling today is from Braid. So I had the idea for the talk, wrote it, submitted it, got it approved to this conference, then promptly shut the company down, and then got a job at Affirm. So whatever, that is what it is. But I think the tech was still interesting. We got into prod. I was really happy with it. And I still wanted to tell the story of what it was. Currently back in IC land and having fun, but this is from Braid days. Okay, so here's the agenda. I want to talk about 4 things. When is what I'm talking about here even worth doing? The easy way to do it, the hard way to do it, and then we'll do a tech demo. I'm actually going to try to cut to some live code here at the end. Hopefully we have some time to get there. The talk earlier today too, shout out to Alex, the talk before was about building a ledger, and this talk isn't about building a ledger. What this is about replicating a ledger. And I hope you don't have to do that, but we'll get into it. But whatever, so a little different. So the question is, when do you do it? Only when absolutely necessary. This talk is about a technical solution to a bad problem. And the bad problem was we had 2 people that wanted to read from the same ledger due to a business case. And I would love for you not to cause that problem for yourself. But I'll tell you the story how we ended up there, which was, okay, so Braid, like most fintechs, you need a partner bank. Our partner bank got acquired and then shut down. So now we need a new partner bank, which I'll call bank number 3. We were working on getting to bank number 3 when they decided they didn't want to do it for a whole other host of reasons. So now we are in a mad rush to get to bank number 4. And the whole way Braid runs, I'm sure a lot of people in this room are familiar with it, was we had an FBO account, so one big pile of money at the bank with a bunch of virtualized accounts under it. And then there's the Braid ledger. We held on the ledger. We were the source of truth. We did all the decisioning, kept the whole ledger on our end. We then, with all of our previous banks, just reconciled that to the bank. Bank number 4, we're in a real mad rush to get set up with them, and it turns out that near ready time for production, we find out that the bank system only works if they can decision certain transactions in real time. So, I see some head shaking. The problem was at this point, we're already so deep, we can't pull out and find bank 5. So the only solution to this problem is get the bank as much information as quickly as possible and allow them to do the decisions that they want to do and then fight that fight later. So me and a couple of my friends, close employees, decide we're going to hack this solution up to try to get to work. And I'm proud of what we got to work. I wish we didn't have to build it in the first place, is the short end of the story. So don't just go do this for fun. But by the number of people in this room, and this just keeps coming up, I've heard a lot of other people have to do similar things, and I think it's just an unfortunate reality sometimes. When we were working on this, one of my coworkers said, yeah, this bank we're working with is like 6 APIs and a trench coat. And it's like, that's kind of how a lot of the stuff works, and sometimes you need to do this sort of thing to make it work. Okay, so you really have to. So there's some caveats here, and like, I'm really just trying to convince you don't want to do this. But so if you can have some lag time, that would be great. We didn't have lag time, right? We were trying to tell the bank, like, let these accounts go negative on your end for 6 hours, for 3 hours, for 10 minutes. And they were like, no. And it's like, come on. So what we really would have liked to do is sync slower, but everything that kept happening to us meant we had to sync faster and have a single source of truth. That's like the rule of fintech ledgers, right? Like there can be a write ledger and then maybe then that would be great if that was the read ledger as well. But in our case, we had ultimately a downstream second copy of our ledger that was a read-only copy of the ledger that was also in some certain situations the truth. Which, yeah, not great. So, yeah. how bad is your ledger data syncing problem? And again, you're gonna sense a theme here, which is our problem was about as bad as I think it could be. But there are ways that your problem could be less bad. So can your accounts go negative? So like I said, there's the Braid ledger we have, then there's our bank partner's ledger. What would have been wonderful for us is if the bank partner's ledger could go negative, because then that would allow us we could blast a fire stream at them of like, I'm gonna send you $1 and then you're gonna send me $1. But the problem with this bank was if those two events got to the bank out of order, you would try to send me $1, now your account's -1 and the bank would, So we actually had to make sure we were sending those two events in the same order to the bank, otherwise it would fail. That was something we were trying to work out with them, but we never quite got to that point where we just let it bounce negative for a little bit of time. And that's where the replay and order problem comes from. And then is the downstream system called sync or async? So a weird hiccup with this bank was that when we made an API call to them and we said, okay, please do a book transfer, move $1 from me to you, the bank would actually just send us back a 200 instantly and then asynchronously move that money, and then we didn't know. So then we'd have to wait and wait for a webhook that's like, hey, it succeeded. So then again, it makes it even harder to sync because now we can't just keep calling their API. We have to call their API, wait for a webhook, call their API, wait for a webhook, and whatever. So for the rest of this talk, I'm just going to assume the hardest case. There's other things you could come up with, but we had to deal with all this stuff. So there's 3 potential solutions to this problem. Let's go through them in order. One note before I get into these things. For the rest of this talk, I'm going to show example ledger entries, and they're going to be as simple as possible. It's going to be a to, a from, and a dollar amount. And that's on purpose because there's a lot of other complicated stuff we're talking about here, and I don't want to get into the double entry accounting part of it, multi-currency, all this other stuff. It's just assume this works with whatever ledger, because our ledger is more complicated than what I'm going to show you, but I'm just trying to keep that piece of it simple. So the first one, I'm sure everyone's familiar with this, the daily dump. So whatever, this whole industry was originally built on batch jobs, right? And so it's tried and tested, nowhere close to real time. And if this talk was called Syncing Ledgers with Batch Processing, I'd be giving it to an empty room. So obviously this isn't what you're here to hear about. But the reason I want to bring it up is if this fits your constraints, you should do it. There's a reason batch processing exists, and it either, it works and it allows you to fix your problems slowly instead of dealing with a stream of errors in real time as stuff all fails. So I would have loved to sit there, and this, like I said, with our original bank, this is what we did, and I would have happily gone on doing that if we were able to. The cursor. So I think this is intuitively where everybody goes next. You're like, okay, we need to do it in real time. What are we going to do? Let's get a cursor. So here's 3 ledger entry items. Let's call them 1, 2, and 3. So number 1 is we sent $5 from bank A to customer B, then customer B sent some money to customer C, and then they sent some more out to bank D. Imagine the first one's an ACH, the second one's a book transfer on our ledger, the third one's another ACH out or something. So with the cursor, what you do is you have a cursor that says, okay, what's the last thing we've synced? We've synced transaction 1. Okay, that's good. We've synced transaction 2. Cool, that's good. You just keep going. But there's a whole bunch of problems here, right? So this is only 1 record at a time. So at some point, it just doesn't scale anymore. Maybe you can do, however many of these a second. It's however fast the downstream API calls are. So maybe you can do 10 a second, 20 a second. So if you start getting sustained bursts of more than 20 or 30 a second, you're just going to fall behind. And that's the second bullet point there, I guess. Can be real time at small scale. But the real problem here is the failure case is really bad because I call it the logjam problem. Let's imagine the second one here, customer B to customer C, fails to go. Until you fix that, you are now syncing none anymore. Because, like I said before, of the problem where everything has to be done in order, as soon as one fails, red alarm bells start going off, and some poor engineer has to scramble and fix that until, you can't skip one. So ultimately, we didn't even build the solution. We just skipped right past it because we didn't want to deal with the failure case of massive logjam every time one transaction failed to sync. So then we get on to number 3, which is before we get on to number 3, I'm going to mention a few things that we noticed about the system that allowed us to get to number 3. So pair of important realizations. 1, transactions may not rely on each other. So look, I just expanded my list of 3 into 4, I added a 4th one there. So the second and third ones in the list, customer B sending their money out, those can't run until the first one does, right? Because that $5 has to come from somewhere before customer B can send it off. But number 6, if you're pulling money off a card, you're pulling $6 off and giving it to customer F, like that's completely unrelated to the first 3 transactions. So you can essentially think of those first 3 things as a group, and then the 4th one as a separate group. So you'll see why that matters soon for the solution here. And then the second one, less important, but it does let us make an important optimization, is that some transactions have no prerequisites. So now I've changed the 4th one here. So before it was card E to customer F, now it's bank E to customer B. So now all 4 of these transactions involve customer B. And so you might say, well, based on what you just said, all 4 of these are related. But the trick is, the last one isn't have to run after number 2 and 3. Because so 1 and 4 are funding customer B's account. Those have no prerequisites. You can run those whenever you want, because all they're doing is building up the balance. So when you're building up the balance, you can just run those right away. When you're pulling down the balance, you have to wait and run after any previous pull downs. So not only can you group transactions like this, so you can run them in different disparate groups, even within those groups, certain transactions can run immediately without waiting for others. All right, so that's the 2 things that let me get to this solution. So introducing the tree queue. I still don't like the name, I'll be honest. I couldn't come up with a better one, and I was like looking around and like whatever. But the reason I call it a tree queue is it is a many queue. It's many queues that have interlinking in between them, and I'll try to talk you through it. So it's a horizontally scaling many queue data structure. And only transactions that rely on each other queue up together. So I'll walk you through an example how this works with like the ledger I was just showing there. So let's imagine, so on the left is our ledger, and we're going to try to sync this to a downstream replica ledger. As this first transaction gets written to our ledger, our database, bank A to customer B, we're going to put it on the queue. So the left side is our ledger, right side is the queue getting built. Okay, so nothing in the queue, put something in the queue, great. Okay, nothing too exciting there. Okay, so now we're going to do 2 and 3. So they're going to queue up together because they depend on each other. And arguably the third one could actually, like the number 2 and 3 could both be children of top one, but whatever, I'm just putting them in a queue because they all depend on each other. The first one has to run, then the second, then the third. But now the interesting part is the 4th one. Card E to customer F, it gets in a new queue because it is completely unrelated. So now you have 2 queues going. You have the like customer B cluster of transactions, then this other one, bank E to customer B. Oops, I labeled that wrong, didn't I? Shit, okay. Let's get to this one. This is the one I wanted to show you. So, oh, that's the reason I put that at the top. Yeah, so this is what I was talking about before. The reason that can go up to the top by itself is it's a funding. So it's like nothing else depends on that one, so we'll just put it to the top and run it. And when we get to the code, I'll show you how this happens. Okay, so now here's a new one. This is, so you have money, so if you follow the tree, here, can I use my laser pointer? Sweet, okay. So you got this one, you got $5 coming in from bank A to customer B. Then that goes from customer B to C, the $3. So you've got 5 in, then to 3. Now customer C over here is going to send $6 to bank E. And so this is actually going to be, this is how it becomes a tree queue, because you have these ones are related down, and then now C depends on these 2, where there's a bank E one here, so it queues up. It's actually in both queues. And so now this one can't run until these 2 do, and that one does. And the way this works is, I call it the next available sync. So when your worker comes through, you're gonna have a bunch of workers that are processing these. They can grab the root of every tree, or the first one in the queue. So when the worker comes through for the first time here, sorry, I'll give this half the room some love, I'll point at this screen. Okay, so this dotted line is what is workable. So we come through, the workers can grab the 2 roots of the trees, chop them off, run them, process them, sync them to the bank, and then everything gets moved up. So now this one and this one, well, customer B to customer C here will become the root. So then now this is what's left of the tree queue. And now the next worker can process just this one because it's the only route. And then that'll leave these two, so the third tick of the worker coming through can grab those two. And then the other interesting thing here is you might think, well, and this is where this system's viability depends on your data structure. So for Bray, the company we were running, this tree was very, very wide and not deep. Because we might have hundreds of customers transacting in any given minute or hour, but they might only move money once or twice, right? I get some money from you, I give it to you. That's two. So now there's going to be a tree that's 2 nodes deep, but hundreds of nodes wide. So every time the worker comes through, there's hundreds of things it can process, then everything gets bumped up 1. So you can have a ton of throughput, most into the point where we could have a lot of workers. So when this tree, imagine this tree is 100 queues wide. The worker might only be set up to grab 15, right? So he grabs 15 of them, and then the next worker comes through, gets 15. So you can actually scale it to a lot of workers and get a ton of throughput, where if you went the straight cursor route, you'd only be processing 1 at a time. This way you can process. Often we would see, if we had 100 nodes sitting in this tree waiting to get processed, we'd see 50 of them get processed every time. So it would clear out very quickly. Yeah, so it allows for transactions to be replayed in order only when it matters. It's maintaining information in the queue about which transactions depend on each other so that you can only run the ones in order that matters and then run everything simultaneous in parallel when that order doesn't matter. Oh yeah, the other thing, so with the cursor problem, I was calling it a log jam. When something fails, it backed everything up, right? So an interesting process here is, let's say the bank E to customer B one failed. Where's my laser pointer again? This one. If that fails, these 3 all can run, right? So it makes the logjam much smaller. So if my ACH transaction, my bank fails, well, sure, then anything else I'm going to do downstream will fail to sync until we fix it, but all the other customers are unaffected. So that was the other goal of this system, was to allow partial degradation, right? Something might be broken, but most of the system continues to work as a whole. And like I said, you can add many workers. There's a lot of parallel processing that can be done here, so you can run a bunch of distributed workers. Okay, so I'm going to get into demo time. I just want to stop. Does that make sense? Does anyone have any questions? I'm happy to take questions, and then we can get to some running code. Yeah, right back here. Okay. Okay, let me take the first one. First, you said proximity?
Yeah, how those relationships between nodes are.
I'm trying to get to the bottom. So the question was, how close are the nodes proximity-wise? Not really. Only what matters is the parent-child relationship for the processing of the nodes. And so when I first did this, it's all, and also you'll see in the first demo, it's all in one SQL table. So it's the data storage itself isn't super distributed out. And then can you repeat the second question, please?
And then just from if it gets halfway through processing a tree and it's done the penalties and fails, do you then re-ordering that tree?
Yeah, so that'll actually be really clear. The first example I'm going to give is in Postgres. So the question was, sorry, I should repeat this for posterity and the other folks in the room, is how does idempotency work and how do you make sure that you're not reprocessing it? So the SQL-based solution, you actually use a lock. So you take out a lock on it, process it. If you fail to process it, you just roll back the transaction and it throws it right back in the queue. And then actually, in that way, the tree structure is not changed at all because it just sits there. And I'll show you an example of that. That's the question up here.
Yeah. Are you using the queue ADT or are you implementing a queue-like data structure in the table you are mentioning?
Cool, yeah, so the question is, are we using some queue software or ADT or just making one? So for Postgres solution, I just made my own queue, and that was when we were working at a relatively small volume, and I'll show you that. The second solution is more theoretical in nature because I haven't run it in production. The Postgres solution ran in production. The second solution I have is a Kafka-based one, which in theory scales to however many machines you want to throw at it.
Follow-up, right? So if it's Kafka-based, right, isn't it very resource-heavy considering there will be many queues used, or?
Yeah, but the Kafka solution, you actually do it. So the question is, how many resources are you using to go with Kafka? Yeah, and it's You end up with 2 topics and 2 tables if you're familiar with Kafka, but I'll show you that. So you don't end up with a new Kafka topic for like every one of these queues, which would be kind of insane. So yeah, I was trying to like avoid.
But queues will be different, right? Like every vertical one will be a different queue.
Every vertical one will not be a different queue. So well, yeah, we can get through that. Other questions? We got one right here.
Do you ever restructure the tree if you got a new transaction that could be a root for a failing transaction?
Okay, so the question is, do we ever restructure the tree when we get a new transaction that could help a failing one?
Yeah, like a second funding.
Yeah. So whenever we got a funding, we just put it as its own queue anyways. Because fundings are just like, they're never gonna, if you run a funding one early, like outside funding coming into the system, it's never gonna break something else because you run it early. So yeah, like maybe your account ended up negative because you got an ACH return, and then, then you chose to fund it again. We'll run that funding, and then maybe us retrying the broken one will now work because more money came in. So yeah, that's kind of like just an inherent property to like, especially the SQL-based solution, yeah. Cool, we good? Oh, one in the back over here.
Yeah, so I think there's a use case where the order of the funding actually does matter, or ordering of payments against a loan or the structure. When you synced it, did you they use the timestamp of the sync as a source of truth, or did they rebuild the real-time timeline using the timestamp of the transaction itself?
Yeah, so the question was, the time of payment matters, right? And so we actually, each one of these had has some metadata on it, and I'll show you that. And then so we actually, we were syncing downstream to this bank, and we actually gave the bank the like actual metadata of our real transaction, and they didn't even know we were doing this queuing thing. This was just sort of our way of facilitating us blasting them all of our ledger data. All right, I'm gonna cut over to the IDE. We'll do some more questions later too, and then so demo time. We're gonna do first in Postgres, which, like I said, is the thing I've actually run in production and have some confidence in. The second one is a Kafka one, and the reason I added the Kafka thing is like I kept giving demo versions of the speech, and everyone's like, "So what are you gonna do when Postgres breaks?" And I was like, "We'll see when we get there." So I spent a little time for fun theory crafting out a Kafka one, and it works. I just want to talk about it because I think it's, at least I can preemptively answer that question with, do you have to just give up on this approach at some point? So let's cut out of this, go over to my happy place, IDE. We just gotta do this. Oh, and I meant to tell you as well, at the end here, I'm gonna put up some links. All the demo code I'm gonna show is in a GitHub repository. You can go take a look if you want. So don't feel like you need to like take pictures of my code while I'm trying to do this. Okay, so first, this is the table. So this is kind of the answer to your question up here. So actually, that is so small. Let's bump the font up a little bit. What if we go to 28? Can we get it all on there? Okay, cool. Is that legible at the back? Should I go bigger? Okay, cool. Glad everyone's got decent eyesight back there. So ID, we don't really talk about it, primary key. Event type. So this is kind of involved in the question we had over from this side of the room, which is we would tag these event types because we were going to treat different events differently. So the event types we used was like, is it a book transfer? Is it an incoming ACH, like ACH credit? Is it an ACH debit? And that would allow us to do these certain optimizations where we're like, hey, when it's an ACH credit, we know we can run that right away. So we keep this extra information about, because everything's really just a ledger entry, but this gives us some extra information about different ways we can process it. Status, you'll see that in a second. The status is really the queuing thing though. Is this waiting to be processed? Is it being processed? Did it fail? Is it done? Prereqs is what I recalled people higher up the tree than me I'm waiting on. So these are gonna be other IDs of this. Axon, we can skip for now. That is part of the tree structure. The data, this is the metadata. So the way we would use this is we would put like some IDs in here and different timestamps and stuff, and effectively this is what we would pass on to the bank then, or use to get the data we pass on to them. Post-processing required, I'm not gonna talk about today, but I left it in here just because it solves a problem I mentioned earlier in the talk, which is some of these things we can't process in real time because I mentioned how like the bank would have to give us a webhook. So sometimes we would put this status into a, yes, we processed it, but we're waiting on a webhook. And then this would give us the information about what webhook we were waiting for. Once it came in, we would dump the status over into done. For the demo today, though, I'm just skipping this because like it's a little gnarlier, and then just whatever, some metadata. So we're going to create this table. Cool, we made it. And then there's a bunch of performance optimizations you can do, but the obvious one is to create an index on status. Because the way the queuing structure works, you're often going to be saying, give me everything in the queue that's waiting. So you need this index so it can just like not have to do a full table scan to like give you what's waiting. And one other thing I'll mention here is like, if you're doing a lot of volume through here, of course you're going to end up with like millions of rows that are status like finished or done. And we just backed this table up and truncated it on like a weekly basis. So we just sort of used it like a rolling log and shifted everything off because there's no reason to keep millions of done records in here. What you really care about is the ones that are like waiting real-time processed. Okay, so I'm gonna run through the couple different operations here. So this is insert. So when you insert into the event queue, you're gonna insert a type, a status, some data, who it acts on, and some prereqs. The type is that string I was talking about. To start with, I'm going to use this account to account type. So this is like a book transfer, or internal transfer. It's the simplest one to talk about. Waiting, whatever, that's what we called it. That's the status. It's waiting to be processed. We use the little JSON B column just to be like whatever metadata you want. So this is what we would do is we'd have some different IDs in here and timestamps and whatever we need when we process this event to act on. Acts on is, like I said, here's the example acts on. It's going to be an array of people what we act on. So it's going to act on account 1 and account 2. These are really just hashes. So actually in our system, the actual system, they were just like MD5 hashes. And it's just any sort of, whatever you want it to be. So in this case, it's 2 internal accounts. And then the interesting bit here is this is actually an insert from a select in Postgres, if you're familiar with this. And it's going from a where clause, selecting back onto the event queue, where anything is in this waiting, processing, or post-processing states, and it acts on this same array. And this is sort of insane bit of Postgres weirdness. This does not mean and. In like every other programming language in the world, that means like and these two things together. In Postgres, this means this is an array, and this is an array, and it returns true if any items in either array overlap. So imagine, okay, if we have this one, it'll be like this and this. This returns true, because obviously they both have overlaps, they're identical. This returns true, because they both have account 1. And then this returns false, because now there's no overlap. So what that does is allows us to build the tree structure, right? Because you're saying, is anything else also waiting, or in the act of being processed, that has any overlaps in who we act on? So if I do an insert here, I'm going to insert account to account 1 to account 2. I'll insert it again. Let's say we have an identical, well, let's make it a little different. So we're going to go from 1 to 3, execute, and then we'll do another one that's just do like 10 to 11 or something different. Okay. 11, and then execute. So if I pop over the database here and show you, we have 3 rows in the database. All are account-to-account events. All are waiting. These 2 have no prereqs. So those are the root nodes of the tree. This has a prereq of 1, which means this one cannot run until this one does. So if I do another 1 and 3, and this is why I like the SQL solution, because I think it's like legible. It's like you can look at the database and like, what's going on here? Where you lose some of that when you get to Kafka. Just a teaser. So we do this. Now we have another 1 and 3. This one has prereqs of 1 and 2. So he can't run until these 2 rows do. So that's that. And then I'm going to show you one more thing. So we also have this, that's the first insert. I have the second insert called insert subset of prereqs. And so what this one is, same insert query, except for you can say, I only care about certain prereqs. And this is like the funding case. So what I can do is, so we have a bunch of people in here who are waiting on account 1 and 3. But I can come in here and say, okay, we're going to go, this is a funding ACH, so an external account to internal account. And let's just say it comes from external account 1 to account 1. But it cares about no prereqs. So if I run this and come over to the event queue, you will see there's this new event. It's also waiting. But even though it depends on account 1, which is waiting in all these other cases, it now gets no prereqs because we've decided for a performance enhancement here, we're going to just, this specific event type doesn't need to wait on prereqs, so like just go for it. Okay, so now we got all this stuff sitting in the queue. The important bit is the processing, and this is like a really gnarly query. Okay, yeah. So, how are we gonna talk about this? So the first way this works, let's start with the easy part. This query must be run in a transaction or you will have a bad time. So the way it works is, Postgres has this thing called select for update, which I put a blog post in here, so if you grab this code and you wanna look at it later, what you're gonna do is select for update everything that's waiting that is a root node. And so what Postgres does is gets row level locks on all of that stuff. And so you're gonna start a transaction, you're gonna come down here and you're gonna go, where is it? Yeah, for update, skipped locked. So it's gonna select for update and lock all these rows and then skip the ones that are locked. And so if you have multiple workers running, they won't step on each other because they're all gonna skip each other's locks and lock their own rows. And what you're looking for is where the status is waiting, you're gonna set the status to processing, where the prereqs are empty, or all the prereqs are finished. I won't talk you through who this whole one, but it's actually self-selecting from the table, and that's what the 0 equals is, which is like are all the other your prereqs set to finished. So I got the transaction started. I'm gonna hit this. Okay, so now we get 3 rows. These are all the root nodes. They're all now set to processing. And here's the events. So now our worker is actually going to do the work of processing these. And if you go over to the event queue, I can prove to you this is running a transaction because these are all still waiting here because this is in a different transaction, so it wouldn't see that yet. But if I ran this query again, these 3 rows that just showed down here are locked, so you wouldn't get it again. And then so what you do is so now we're processing and working away on it. Oops, I forgot to get the IDs though. They are 1, 3, and 5. So the query you're going to run is update event queue, set status to finished, where ID is in 1, 3, or 5. So you run that in the same transaction. And this is the question we had over here about how do we know when something failed, is like if it failed, we would actually do, maybe it was 5 failed, we would just do set status back to waiting, or we could set it to failed, whatever you want to do for your error handling case there. And then you can commit. So now, if we go back over here, we have 3 finished, and now 2 are waiting. They have prereqs that should be done now, so let's start this whole thing over. The next worker comes through, start a new transaction, do this. Okay, now we got 1, so we're processing this one. That is number 2, so we're done processing it, set it to finished, commit. And then we do it another time, we should get the last one. Boom, so now we're processing this one, number 4, because both of its prereqs are done. Set 4 to finished, commit it. And then now if we do it one more time, oops, well, we start a transaction, I'll be right. And then hit it, it should be empty, because everything's done. So if we go back over here. And so that's the the worker just gets no results, and then you know there's nothing to do. So that's the basic way it works. Questions about the SQL insanity over here? Yeah.
If your application dies, don't you lock your entire database?
Application dies. You set a timeout on it. So the transactional timeout in 10 seconds and auto rollback, yeah. Sorry, I shouldn't repeat the question, which is, can you just lock your entire database and then just be in a deadlock situation? And in practice, yeah, you just set shorter timeouts. Cool, well, I got 5 minutes before we're out of time. I'll take you through my theory of how you change this to Kafka. It's whatever. I'm not thrilled with it, but I do think it works. So I have a series of, so I actually tried to write the code in Kafka, and I realized the code is even more impenetrable than what I was just demoing here. So I was I'm not gonna just put this nasty Java code up on the screen and try to talk you through it. So I just have a series of files that sort of talk about it. So first one, can I get a show of hands, who does Kafka stuff in the room? Because I'm gonna okay, cool. So I guess we got a few people here. I am no Kafka expert. I wanted to use this as an excuse to learn it. So the one thing I'll tell you about Kafka that's interesting for this example is there's 2 topics in Kafka. There's streams and there's tables. And so the way I understand is think of how you could describe a game of chess. A stream for a game of chess is, this square, 1-1, 2-1, 3, like pawn from 1-1 to 1-3, whatever. And then you could describe a chess game as a stream of those moves, right? And you would look at it would be one long stream, and to figure out what happened in the chess game, you have to read through the whole stream. The table is, okay, we'll read through that whole stream, make a chessboard. Then the chessboard's the table, the stream is the list of moves. And so Kafka supports both of those things, even though they're ultimately both based on streams. The table is just like a realization of the stream. So to make this work, you kind of have to do both. So this is a stream of ledger data, right? This is sort of what we were looking at SQL. So you can imagine blasting these events off to the Kafka stream. It's account 1 to account 2. I'm just doing this in cents. So $1, it's waiting. And I did T1, so it's just transaction 1, transaction 2, same thing. So you get these all blasted off into the topic. I just call this topic ledger events. So it's every time an event happens on your ledger, you put it in this topic. Then you have to make a table of those. So you're taking that, and this is the chessboard example, right? But you're going to make it into this table. You're going to filter. So this is sort of some pseudocode. It kind of looks like the Java code would. So you're going to filter out anything where the status is not equal to waiting. I have that backwards. So, no, yeah, I had it right. Okay, why am I second guessing myself on stage? But so you filter it out just to waiting. Then you group it by the ledger. And there's actually going to be two tables. Because there's the to and the from, but I'm just showing it as one here because whatever, we don't have a ton of time and it's easier this way. So ultimately you end up with this table that is a key value store, right? So the key is what is it operating on, account 1, account 2, account 3, and which transactions are waiting on that. So account 1 has 2 transactions about to act, that are waiting to act on it. Transaction 1, transaction 2, account 2 and account 3 both have transaction 1. So this is it's this super simple tree, right? Because from what I was showing before, like essentially this one is waiting on this one, and that you can see that here because it's behind it in this list. So you make this one table off of your ledger queue, or ledger topic, then you can make this other table. So this is the same thing, you filter down to waiting, because you don't care about done ones, and you make it into a table, and this one is just key valued off of the primary key. So transaction 1, transaction 2. And then here's where it gets really gnarly, which is, so here, I just put the 2 tables here again so you can see it. Kafka has a concept of a thing called a join, which is just like an SQL join. And actually, to make this work, you have to do a left join. So you left join this table to this table. And what you end up with is which accounts are relying on, which, I call them instruments here because it could be a card, a bank account, internal account, are relying on which transactions. And you join it over to the to and from up here. And ultimately, you're going to get a result that looks like this, which is for transaction 1 to run, you need transaction 1, then 2, then 1. So this is actually the tree right here. So transaction 1 is the root node here. It's also the root node here. Transaction 2 is not the root node here. It's actually secondary. So this one can be run now. This one cannot. Nope. Because you need to be the first in all of your nodes to do it. And then a note on partitions for like the 3 people who raised their hand who are like Kafka people. Like Kafka does like a sharding thing, like partitions. And to make this work, to do the join, you have to do your partitioning smart so that you don't end up with different data on different shards and you can't join it. And like that's a whole gnarly thing I'm not going to go into right now. But to make this work, you have to like make sure you get trees that are going to rely on each other on the same partition. But so now we know we can run this one. We can't run this one. So we're going to blast off a new event to our workers to say, hey, process this one. And that is topic ready to process. So now you're just going to blast the same event off, but instead of up here, you're just getting every event. They're getting all blasted off. Down here, it's just, which ones are ready to run. So this one's ready to run. Worker gets that. Now it's kind of like simple streaming stuff, right? You get an event, you process it, you sync it. So then what the worker does is processes T1, runs the actual sync logic to sync it downstream, and then produces a new event back to the topic ledger events, which is just done. And then that actually will allow the next one to run. So sort of a similar flow to the SQL one. It's just, you have to do a little more tiptoeing around the fact that like Kafka's pretty stateless, whereas like in Postgres, I'm really able to like lean on the like statefulness of the database. So I feel like that's a lot to just try to do in 5 minutes super fast, but I don't want to go over too much anymore. So like I said, I'm going to go back to PowerPoint. Slideshow, play, oh, not play from start. Oh no, okay. Get all the way back through here. Okay, so I want to put this up there. So it's my email, that's my GitHub. If you do the QR code, it literally is just my email, my GitHub, my LinkedIn, so you can grab it there. And got questions, ask me, I'll be around for a bit. And the code samples are all there. You can send me an email if you want to know anything more about any of this craziness. And thanks a lot.